Will appear in next month's issue of Physics Today. All right, Belenkiy. Titles on the screen.
Thank you, Joe, for a nice presentation. I will talk about the man whose motto was this quotation from Dante, which I don't take a risk to say in Italian, but translated in a poetic way would be, the waters I'm entering, no one has crossed yet. At first I didn't expect to have 25 minutes. I thought I will have much less. So I thought to skip all the bio info and some mathematical details, but since I have time, I decided to. I thought also that I will speak mainly before historians of science, and since here there are many distinguished astronomers, I would mention several facts from his biography as well. So the major, he was raised and born and raised and studied in St. Petersburg University, and met and learned from Paul Ehrenfeld, in particular, and Vladimir Steklov. He took part, he served in Russian army in the First World War, and he taught and developed theory of ballistics. He was awarded a military cross for his service. Then he got his first professorship far from St. Petersburg, near Ural Mountains, during the revolution time. And he came back after the Civil War was over to St. Petersburg, 1920, and became a member of Geophysics Observatory in St. Petersburg or in Pulkovo. And later he became director of this observatory. In parallel, he taught in several places, and particularly in St. Petersburg University, taught mechanics, aerodynamics, and meteorology. In fact, he was famous as a meteorologist, and he took part in 1924 in International Congress somewhere in Netherlands, and was a member of executive committee. Many famous applied mathematicians sent their letters and necrologies to contribute to necrology after his death in 1925 from typhus, which he got in spending his honeymoon, in fact, in Crimea. A month before his untimely death at the age of 37, he made a record balloon flight to the height of 7,500 meters. I thought it is a world record flight, but recently I learned that Frenchman made a little bit better, but probably this was the flight when all participants came back alive. In French flight, 2 out of 3 people perished. And he described, he was also on the brink of death, and he describes his experience in an article before, which was published after his death. So he was an accomplished man, and it's amazing how much collected works of him had memories of Vladimir Fogg, of Yakov Zildovich, Pyotr Kapitsa. But his fame, of course, rests on 3 and two papers which were published in Central Journal, a journal, a physical journal, journal of the 1920s, 1922, 1924. And I'll describe right now, describe his results. They are widely unknown. In fact, they are not only unknown, there is already a big chain of wrong references. And because of that, because of people are uncertain, in fact, what he accomplished. And they are, I believe, a bit embarrassed to quote him and to give him the credit he deserves. Here is an example, by the way, not to be just talkative. The book Discovering the Expanding Universe by Harry Nussbaumer and Lydia Pieri, published quite recently, a very distinguished book, a very accomplished book, which I believe would be a textbook of this on history of accelerating universe for a long time. Its cover has this number, 5 photos with 6 people on them, and of course you can recognize, you saw them today. Hubble, de Sitter, Einstein with Lemaitre, even Vespa Slifer is present, and Arthur Eddington, and Friedman's photo is missing. And the book gives enough credit to Friedman, but I believe that outsider looking at this cover would have quite a different opinion about Friedman. Not counting him among the major discoverers. Even the essay Accelerating Universe, you probably know that Nobel Prize usually accompanied by what is called a scientific background of the Nobel Prize in Physics. So it is compiled by the class for physics of the Swedish Royal Academy of Science. So what it says, in fact, this essay issued a year ago, it ascribes to Friedman, a first paper of Friedman, the discovery that Einstein's steady-state solution was really unstable. Next, it asserts that in 1924, Friedman presented his full equations. And next, it states that in 1927, the Belgian priest and physicist Georges Lemaitre, working independently from Friedman, performed similar calculation based on general relativity and arrived at the same result. Needless to say that all 3 statements are wrong. The first is just misattribution. The second is he presented his full equations in 1922. And the third statement, at least in the second part, arrived at the same results. It's of course a wrong statement, huge exaggeration. So the point is not to pick up these petty mistakes here and there. The point is that it doesn't give Friedman a credit he deserves. So let me start explaining what Friedman really did. Again, I didn't want to scare people with Einstein's general relativity equations, and but now I do believe that I have to say several words about that. So general relativity equations is 16, or rather 10 because of symmetry, 10 equations, very highly nonlinear. They include products of second, first derivatives. And this is equations for metric elements. Metric, how you measure a distance in time-space. There are 4 components, of course, because there are 4 3 space and 1 time coordinates. And then you have so-called tensor, 4x4 tensor, and eventually 10 equations, which can be reduced in some cases. And what Friedman did, in fact, he took, I also don't want to discuss in great detail situation with which was between 1916 and 1922. But you heard all the talks before me, and you know that there were two solutions, one by Einstein, solution A, and solution B by de Sitter. They were slightly different, but de Sitter had some very advantages and disadvantages sides, and people usually, all the workers in the field, all the names fortunately you heard yesterday and today, all those who are mentioned in the essay of this essay composed by a class for physics, in fact mostly Swedish names, they didn't mention de Sitter, they didn't mention Silberstein. So yeah, but these names were fortunately mentioned, say, in the talk by Cormac Rafferty yesterday. So I don't need to present these names again. So after you work with the STEM equations, you can squeeze them into two equations. One is second order, ordinary differential equation. The second is first order. So when you, and Friedman first who suggested the general framework, when the curvature of the space might be changing, means that radius of the spherical space can be increasing, and therefore you can talk about expansion. This was suggested in 1922 paper by Friedman, and as a result, he instead of just verification of identities which did Einstein de Sitter in their solutions, he got equations for this radius of expanding universe, and they recently, quite recently, they became known as Friedman equations. So in a sense, same is coming behind Friedman, but you see, not he didn't get yet full credit, as I will maintain throughout my talk. So he discovered Friedman equations, and moreover, he proceeded solving them. And as I said, he was applied mathematician, and applied mathematician always likes to bring solution to a number. So, and he gave numbers wherever it was possible. So you see that when you integrate the second order differential equation, you immediately acquire a constant of integration. This constant A, you see it here. Then you have to compare this integrated second order differential equation with the first, and you find that A is nothing more than relation of K. Kappa is Einstein constant, just consider it as a constant throughout my talk. Rho is a density, average density of universe, and R is this expanding radius to the cube divided by 3. It's an exact solution. And then when you realize that volume of three-dimensional sphere is nothing more than 2 pi r cubed divided by 3, you realize that this is proportional to mass of the universe, because you have here volume times density, you have mass. So you can think about A as something related to mass, but in fact it has dimension of radius, and in a sense it's gravitational radius of the universe. So what is important that when you see solution cannot be presented in quadratures, you have to keep an integral, and very in somewhat inconvenient form as t time equal integral from r0 to r root square x divided by cubic. And here is second constant of integration. And Friedman is saying first that when r is equal to r0, this is 0, and t equal to t0, and t0 is nothing else than h of the creation, h of the universe, time passing from creation in his book. So now he analyzed all the paper dedicated to analysis of this expression, y, Because, you see, a physical meaning this expression has only if expression in denominator is positive. So, because x is positive when x is more than 0, then this expression is positive, not always. It depends on a relation between all coefficients which are in the cubic. So what is the cubic, in a sense, is fundamental. And in this paper, Friedman realized that this coefficient before x cubed, it is represented by cosmological constant lambda. Now lambda is written as a capital lambda, but in Friedman's time it was small lambda divided by square of speed of light. And a free term is nothing more than mass of the universe. This coefficient would be clarified later. So again, Friedman realized that all behavior and all possible solutions of this equation, this expression depends on behavior of the cubic, positivity of this cubic, and I will proceed with describing what could happen with that. And what could happen is that these coefficients are in different relation versus each other. First, and this was Friedman's major, one of the major discoveries. That, again, he didn't, was not involved in the discussion which solution, Einstein's of de Sitter or de Sitter, is better. He started with just a general framework. He said, let us assume that universe is homogeneous and isotropic. Then he took a general metric for that. And he arrived at general equations and then at a solution for this equation. He assumed that cosmological constant is an independent parameter. This was a huge leap already in understanding of what is going on, because in Einstein's and de Sitter solution, lambda was linked to the radius of the universe. It was not independent. And even Lemaitre, 5 years later, made lambda be dependent on radius, initial radius in Lemaitre. So everything depends on size of lambda. If lambda is more than expression here, which I call lambda critical, which is speed of light squared divided by mass squared. So if lambda is greater than a certain value coming from this expression, then the universe is expanding and can be born from singularity, and it has two phases, deceleration and acceleration, with inflection point which can be calculated. I give this calculation, but it's trivial in fact. You can look at the cubic and calculate that. So look here, what is going on? You see, when lambda greater than lambda critical, this is cubic, just a cubic as a function of x, and cubic with a positive coefficient before x cubed looks like that. Of course, it can cross x line 3 times, but the question is how many positive roots it has. Here, it doesn't have any positive roots. And because of that, cubic is positive from 0 to infinity. And this is defines the first scenario which Friedman describes here, and he calls it monotone world of the first kind. In fact, expansion universe of the first kind. You see, it starts from singularity here, the first derivative is infinite, then it goes like that. Here is VR at t0, but here is a flex point, and then it accelerates. Here is over deceleration phase, and here is goes acceleration phase. But he proceeds with discussing another case when lambda less than lambda critical. In this case, you see a cubic has 2 positive roots, and it's positive either here between 0 and x1 or between x2 and infinity. If it's positive, and if you take a situation, it cannot be, you cannot be here. Radius forbidden to be in this segment. You can start from this point and go exponentially to infinity. He calls this scenario M2. In fact, it starts from radius equal to x2, finite radius, and goes accelerating toward infinity. Or you can pick up, if you wish, you have to find this from observations where you are, this segment from 0 to x1. But look, this allows you periodicity. You start from 0 and go expanding to radius x1, and then you have contraction phase back, and so you can go even infinite number of times here. He calls this solution periodic solution. Okay? So Friedman's statement was clear statement, clear understanding of what is going on. We don't have astronomical data to decide which of three scenarios is true. We have to learn it from astronomical data, future astronomical data. So he also discussed what is called a critical value, lambda equal to critical value. In this case, you have a cubic has double positive root, and this makes a logarithmic singularity, and it implies, depending where you are, if you are here, you go from 0 to a certain radius, x0, infinitely long, logarithmically long. Or you're starting from double root and go to infinity, and it means that you start somewhere on this x0 in minus infinity and infinitely long go as an exponent increasing radius. Friedman had also interest in topological ideas. In fact, he made a crusade against an assumption by Einstein that universe is spherical. Einstein was so much in this scholastic mood of thinking, and his theory, math, philosophy, demanded that universe would be finite size. It means that spherical. And it was Friedman who raised his voice against infinite universe. And at first he suggested that universe, I'll skip these 2 points because I don't have much time. He suggested that the universe not necessarily spherical, but can be a space of directions, which is half of sphere S3. But the major thing here, that he says even it's spherical, even metric comes from a sphere. It's not necessarily finite, because it could be coverings of this sphere. Imagine that you have a plastic wrap, you wrap it around the sphere. So you have, in fact, infinite number of leaves. Volume is infinite. Even the metric is a metric of a three-dimensional hypersphere. But in 1924, he gave a better solution. On advice of his friend Yakov Tamarkin, a famous mathematician, he found that another solution is possible, that universe can be curved negatively, that not spherical metric, but hyperbolic metric will work. And he again proceeded and again, you see, solution is almost the same. What changes is the sign before linear term. So this cubic, he discovered that cubic is really fundamental. Not only these two coefficients come from are fundamental quantities, but this is tells you what is the curvature of the space. Plus when it's negative curvature, and minus what is positive curvature. When curvature is 0, where flat space, you have here 0. So okay, Friedman made had some ideas how to check curvature of the space empirically, and he had some interesting ideas of triangulation of the universe, sending beams of light to spiral nebula, by the way. And I learned later that Lobachevsky had this idea, founder of non-Euclidean geometry, and later Karl Schwarzschild. Friedman was unaware probably of that, of their contributions. Because you see what's happened, that what Friedman did is extremely important lucid, but in the last years, historians narrowed the historians who discussed who discovered expanding universe narrowed the race to two people. It's like a final race. There were semi-finals, and Friedman didn't come to, in their opinion, to finals. So the final race is between Hubble and Lemaitre, and several publications announced a winner. Lemaitre is a winner. So let me say, in fact, what Lemaitre did briefly to compare with Friedman. At first, in 1927, he realized that energy is not conserved but spent on expansion, because Friedman and Einstein usually solved their equations with pressure equal to 0. Lemaitre was smart enough to keep P non-equal to 0 and realize that there is no energy conservation in this general relativity. Also, he postulated Hubble constant as a coefficient of proportionality before radial velocity and distances toward celestial objects, particularly nebulas, and found that it related to radius of expanding universe. So this is important link between astronomy, empirical astronomy, and Friedman's, Einstein, and Lemaitre's metric. But what he did, what his first idea about expanding universe, here it is. He picked up that degenerate case of cubic, which Friedman discussed, but among as an inferior one among others. But for Lemaitre, it was very important that lambda is linked to this solution, to the radius, and this particular solution, which he believed is initial solution. So here is a solution which was taken by Lemaitre as a true expansion, and this, for many years, he defended this solution as true solution. Let me say two words also what data was available for Lemaitre in 1927. For Friedman, Friedman started from scratch. Of course, he read papers by Einstein and de Sitter, but that's it. And Lemaitre benefited from radial velocities of 41 galaxies found by Vesta Slipher and published by Eddington. This table was already on your view for several presentations. He used Hubble's 1926 observational data for distances to the galaxies, so Hubble's contribution to Lemaitre. And he used, this, I understood that this diagram is unknown virtually to everyone. At least Harry Nussbaumer said that he didn't see this picture in Silverstein's book, not paper to which many people refer, but on the last page of Silverstein's 1924 book, there is this attempt not just compute correlations between velocities and radius, but to place them on a straight line, asymptotically straight line. And of course, you heard why Silverstein's approach was not enough, because he in fact tried to defend de Sitter's universe. But I think you know that Lemaitre knew the Silverstein's works, and I believe that his linear equation for H, for Hubble constant, came almost directly from Silverstein. And let me go conclude with several slides. This is a quote from a book by Nussbaumer and Bigeri, which I already mentioned. In a footnote to his 1929 public lecture, Lemaitre thanks Einstein for having directed his attention to the work of Friedman, which, he says, already contained several notions, the results later rediscovered by himself. Thus, Lemaitre owes nothing to Friedman. In fact, the statement strikes me as inconsistent. In fact, the second phrase doesn't come from the second statement doesn't come from this one. Even he Okay, you can make this conclusion on your own, but we exactly know what Lemaitre had to owe to Friedman. Comparing 1927 paper and 1922 paper by Friedman, we know exactly what Lemaitre could have learned from Friedman. And more than that, he owes not only to Friedman, but as we saw, he owes only to Schleifer, to Hubble, and to Silverstein. This slide again reminds you what Friedman accomplished. In 1922, he first, except for his equation, for his metric, linear metric, except for that, these are acknowledged already, as Cormac said yesterday. It's already, he has this immortal fame. His name is attached to the Friedman equations, but independently of that, is realized that cosmological constant is independent parameter and must be found empirically. That universe is expanding, that it may accelerate, it may be born from singularity. And in 1924 paper, he realized that universe can be curved negatively and be infinite. In fact, I believe without this paper, physicists would think many years would pass before physicists would run across an idea that such situation is possible. And probably Einstein de Sitter's paper of 1932 would not happen at all. Because now you can say that, okay, let us take a flat universe, curve 0, not necessarily -1 or plus. In fact, in the question, who is the major person behind discovery of expanding universe, I believe Einstein was not heard. And what Einstein said in the book called Meaning of Relativity. It is a popular book, but in editions 46, 50, 51, it has an appendix on cosmological problem. In appendix it says, when Einstein discusses that he was forced to add a cosmological term in his equation and was unhappy of that because for a long time. And suddenly, he says, mathematician Friedman found a way out of this dilemma. His results then found a surprising confirmation, Hubble's discovery of the expansion of solar system, a redshift of the spectral lines which increases uniformly with distance. The following is essentially nothing but an exposition of Friedman's idea. And for 15 pages, there is exposition of Friedman's idea. No word about Lemaitre. Einstein never mentioned Lemaitre's name, in fact, in his writings. Hubble's, you see, unfortunately, he credited Hubble with what belongs to several people, and de Sitter and Schleifer and Hamilton in particular. And now we are coming to modern heroes, Perlmutter, Rees and Schmidt, Nobel Prize winners for the last year. What in fact they found, what two great discoveries were done by just observations, that lambda is positive and universe is accelerating, and they found this famous ratio between mass and lambda as 0.3 divided by 0.7. So what it means for Friedman, for three worlds described by Friedman, it means that periodic world should go away. Why? Because periodic world is sign, essentially sign. So sign is a decelerating function, second derivative is negative. So periodic world should go away, but these two still compete. You don't know which one to choose. And it was chosen only in 2004. Which universe we live in was clarified not in 1998, but in 2004 by recent collaborators who found that there is flex point. Remember that the feature which distinguishes between two universes which both expanding is a flex point. And it was found by Rees as 5 plus 1 minus 1 billion years ago. And according to Friedman's formula, again, here is a computation which you come to 0.6 R0. Of course, you have to use results by Perlmutter, Rees, and Schmidt that they related as 0.3 divided by 0.7. Friedman himself could not get this result. But now we can get this result just plugging in a formula which comes from Friedman's equations. And you can compute that, according to Friedman, it should be 5.6 billion years ago, which nicely match what was found empirically by Reese. And the last slide, sorry, Joe. The last slide for my talk is the first chapter of the saga of the Big Bang and accelerating universe. The saga, as I would tell it, would be started with discovery of redshift by Justus Leiter, not in 1912, but in 1914. So we have a chance to have another anniversary 2 years from now here. 1915, when Einstein discovered his general relativity equations in correct equations. In 1917, when de Sitter realized that Schleifer's data and Einstein's equations should be put together. 1922, 1924 papers of Friedman, which describe the papers which describe expanding universe, and the very term expanding universe was introduced in this paper of 1922. These papers by Hubble 1926, we know that it's obsolete. A paper by Lemaitre 1927, half obsolete. 1929 paper by Hubble is also, I believe, obsolete. Important observations which convince many people in truth of expanding universe. And 1932 paper of Einstein, half obsolete as well. It's still, universe might be flat, but cosmological constant, as we know, is positive and should not be eliminated from the whole framework. So again, what they claim that among all these papers, only Friedman's papers stand as they are. They should not be changed. One letter should not be changed in them. Again, the results of 1998 and 2004 come as a direct continuation of this Friedman's paper. The rest of the papers, even Einstein's theory of relativity, even his formulas were changed. And of course the papers of Lemaitre were, I believe, were very confused, and he came to a clear understanding of the matter much later. So in this first chapter of the saga of the Big Bang, Friedman occupies not only a central place chronologically, but essentially. I believe this is, if you are looking for a discoverer of expanding universe, here is the man. Thank you.
We can take one question while the next speaker is setting up.
Well, I'm very glad that someone took Friedman in, because he really deserves it. And actually in our book we dedicate a whole chapter to Friedman. And you can also see how much Einstein admired Friedman when he changed his opinion and agreed that the universe could expand. He mentioned, actually Friedman had said it, and he adds something very important: without observational evidence. And you can see a jealousy of Einstein in that. Because Einstein, I'm sure he kicked himself for not having discovered that himself. He could easily have done so. Now, some other points. When Einstein refused Friedman, he refused it with about 10 lines. He said he made a mistake. Friedman wrote to Einstein, I didn't make a mistake. Einstein went again, had a look, and again about 10 lines, yes, Friedman didn't make a mistake. That's all. But not quite all, because in the book we show the draft of what he did. And there he wrote, in addition, to which, well, he said, okay, Friedman is all right with his equations and instability and so on, to which a physical significance can hardly be subscribed. So but then he stroked that out. And when we said that Lemaitre owes nothing to Friedman, then it's because in the translation, which was published in monthly notices, Friedman added a reference, Lemaitre added a reference to Friedman. As soon as Lemaitre had learned from Einstein that Friedman had done these things before, the theoretical, he always gave credit to Friedman. So Lemaitre was quite correct and just in that. And there were people who said, oh, because there is a reference to Friedman in the second page, in the translation, they said, oh, okay, Lemaitre knew Friedman. And that sentence means, no, Lemaitre didn't know Friedman, he doesn't owe anything to Friedman. And that we didn't have, you could write the whole story of discovering the expanding universe without mentioning Friedman at all. It would be great injustice, but you could do it, because Friedman, of course, gave much wider solution to Einstein's fundamental equation than Lemaitre did, or anyone else up to that time. But the actual discovery of the expanding universe, that was done without Friedman.
This is, we discussed, I hope you heard what Harry is saying. He is saying that, in fact, the whole story of discovering expanding universe missed Friedman. And Friedman himself was rediscovered much later. And I disagree with that. I do believe that all this, what is called discovering expanding universe, all this discussions in 1930s, 40s, 50s, they were marked by Hubble's and Lemaitres, by the way, incorrect calculation of Hubble's constant. It was, as you know, because of that, Hubble constant was overestimated by an order of 8, and in fact, age of universe was underestimated by the same order. And Einstein was despaired, in fact, because of this strange short cosmological age of universe, which is coming from Lemaitre and Hubble. I believe that, in a sense, Lemaitre and Hubble were detrimental to the development of this expanding universe cosmology. And in fact, doesn't matter when Friedman exactly was recovered, in 1960s. I'm saying that Perlmutter and others took from the point where Friedman left. They supplied one, in fact, empirical fact, this ratio between omega m and omega lambda, which is just necessary to complete Friedman's program and to answer the final question. So again, I believe that Friedman stopped at the point where empiricists astronomers should say their word, and when they said it, immediately was clear which of the three scenarios described by Friedman is true. So I believe the discoverer of universe is Friedman, and it is, my friend Cormac Rutherford said that photoelectric effect belongs to Einstein. Okay, even it was checked by Millikan some time later. The same with Friedman. Friedman predicted 3 possible scenarios, and when astronomers gave empirical verification, Friedman was fully justified. That's it.
Thank you.